Okay, we are now recording. So welcome to today's session. Our workshop today is Catapulting Math and Science to New Heights. And we have some awesome volunteers who are going to be helping us out with this. So my name is Maggie Roberts, and I am the STEAM in the Classroom Program Coordinator with University of Illinois Extension and 4-H. I am based out of here in McLean. And we're going to go ahead and get started. So I will stop sharing my screen, and then you guys can take it over, introduce yourselves first, and then go from there. Hannah, I think you're still muted.
You were very correct. Thank you so much for letting me know. Okay. Hey guys, I will be sharing my screen with you guys throughout this. Yeah. So this is Catapulting Math and Science to New Heights. My name's Hannah. I'm a junior physics education major at Illinois State. And yeah.
Hello, everyone. Good afternoon. My name is Leslie. I'm a math education major also at Illinois State University.
Perfect. And we will be working through this workshop with you guys. So we should have some fun today. The very first thing that we want to do, though, before we get into the workshop is we want to do a little icebreaker. So we already told you guys just a little bit about ourselves. Like I said, I'm Hannah. I'm going to be a junior, and I'm a physics major. But we also want to know your favorite candy. So, for instance, my favorite candy, I gotta go classic here. I love Hershey Kisses. So Leslie's now going to share a little bit about herself, and then we want you guys to all go around and share your name, your grade that you're going into in the fall, and then also your favorite candy. So Leslie's going to start it off.
Yes, my favorite candy are Sour Patch Kids. Would anybody like to go next?
My name is Deepta. I'm 10 years old. I'm about to be 11, and I don't really have a favorite candy because I like all the candies.
Solid option. I also like all the candies.
My name's Dion. I'm going to be going into 8th grade this fall, and my favorite candies are Jolly Ranchers.
Those are really good as well.
Yeah. Who would like to go next?
My name is Josiah, and I'm going into 4th grade, and I don't really have a favorite kind of candy.
Awesome. That's okay. We kind of put you guys on the spot there with favorite candy. It took me a little bit to think about one too, so I understand. Would anyone else like to share their icebreaker?
Hi everyone, my name is Meg Meeker, and I work for the McLean County Extension and 4-H as well with Maggie. And I'm actually going to be a middle school science teacher in the fall, so I'm leaving Extension, and hopefully I'll learn a lot. My favorite candy is probably Reese's.
It's a good one. Awesome. Thank you for sharing. Is there anyone else that would like to share that hasn't shared yet?
I guess I'll go ahead and share. So my name is Becky Darner, and I am a faculty member at Illinois State University, and my favorite candy are Junior Mints.
Nice. So let's move on then. So before we start this workshop, we're also going to show you guys just a cute little animation of Catapult. So as you guys know, this whole workshop, we're going to be building our own catapult and experimenting with that. So we want to show you guys this little introduction video, which clearly, there we go. So that's our little catapult video.
Yes, I hope you enjoyed that video as much as we did. As you saw in the video, catapults were used to launch objects such as stones or sharp wooden poles in the ancient times. And through this workshop, we will get the same feeling as we will create our own catapult and launch them as well.
Yeah, so they were used in ancient times as weaponry. So the very first thing that we're going to do to start our experiment is we are going to give you guys a couple minutes, about 3 minutes if you would like, to decorate 3 popsicle sticks. Now you're going to be using a lot more than 3 popsicle sticks, but these 3 are the ones that are going to be shown. So you guys can take any markers, I have markers over here, or colored pencils or crayons, whatever you'd prefer, and decorate 3 popsicle sticks in whatever way of your choosing. So we're going to give you guys just a few minutes to do that. And if you want to show us how you decorate your popsicle sticks, I am all ears. I would love to see your decorated popsicle sticks.
You can decorate them any way you'd like as well.
Yes, I'm doing polka dots on one of mine.
Nice. How are everyone's popsicle sticks looking?
Looking
Oh,
good.
I like it.
Ooh, I'm a fan.
I went towards more of a smiley face look.
Me too. I did different smiley faces
Nice.
on one of them. And I did polka dots, and then I did butterflies. We're going to give you guys just one more moment to finish up decorating your popsicle sticks, and then we will move on. How are we doing, you guys? Do we think we're ready to move on to the next step?
Yeah, I'm done.
Ready?
Perfect. Let's
I'm
move
your
on.
parent on mine.
Oh, I like it.
Oh, nice. Those are very cute.
Thanks.
You're welcome.
Okay, so the next step is a big one. So this is going to be how we actually construct our catapult. So we're going to take it through step by step, and we're going to do each step with you guys. So to start us off, this is step 1.
So for our first step, we're going to use 12 popsicle sticks. We're going to stack them all on top of each other. So let's 12.
Okay. Stack 12 on top of each other.
Yes, and the very top one should be one of our decorated popsicle sticks.
Okay.
Yes, now that we have that, we grab one of our rubber bands and we put it on one side and wrap over the sticks,
I don't have it.
the popsicle stick. Here we go. The distance does not matter where you decide to place the rubber band. That is your choice.
Yep, you just want it to be towards the end. So how far from the end doesn't matter as much. You just want it to be towards one end, though. So like how Leslie is showing you and how I am showing you.
How tight should they be wrapping it? Should it just go on one time, or do they need to twist it around and loop it a couple times?
It depends how big your popsicle sticks are. For me, I'm able to do it 3 times, so you should have it pretty tight, not too tight where you're afraid it's going to snap if you do it another time, but you should be trying to do it multiple times if your popsicle sticks allow. Leslie, how many times did you do your popsicle sticks? Because I know you have big ones.
Yes, I also did 3 times.
There you go. Correct. So 3 times is probably a pretty standard tension for it. Perfect.
Nice job.
Move on to the second step, and at any point, please let us know, okay? So you can stop us and you can go, oh my goodness, wait, you guys are going way too fast. I'm still stuck on step 1. So let us know if we're moving too far ahead of you, okay? We want to all be at the same pace. So this is going to be step 2. So you're going to slide a new popsicle stick, and this is going to be one of your decorated ones, over the bottom stick perpendicular to the 12 popsicle sticks. So you're going to take this stick, the newly decorated one, and you're going to place it over the last popsicle stick, so underneath 11 popsicle sticks, and it's going to be perpendicular, which means it's going to make a right angle, which is a 90-degree angle. So for instance, if I take these 2 popsicle sticks, and one is vertical, facing totally up and down, and the other is horizontal, and you put them together, this is perpendicular because they're creating 90-degree angles, which are called right angles. So you're going to put that decorated popsicle stick perpendicular to the other popsicle stick. So it's underneath 11 popsicle sticks, and it's just over that one bottom popsicle stick. Does that make sense? Let me know if you have any questions, and this is what it should look like. So that newly decorated popsicle stick should lay straight up and down vertically, and it should be underneath 11 total popsicle sticks.
Can you show me that again? I didn't understand.
So you're going to take your decorated popsicle stick and you're going to slide it underneath 11 popsicle sticks. So you're going to create a tiny little opening between the bottom popsicle stick and the 11 popsicle. That to be perpendicular, so you want it to make a 90-degree angle with the other popsicle sticks. So if all of your popsicle sticks are lying left to right, like they're lying down, then you're going to have one that's standing up stick straight. Yeah, just like this. So I have 11 popsicle sticks, and then I have my one perpendicular popsicle stick, and then I have one more popsicle stick right underneath it.
Okay.
Yeah, that looks awesome.
We want to place it also a little bit more towards the center. Like
Yes.
right
so
in the middle.
Yes. Perfect. Thank you, Leslie. You want that new popsicle stick to be right in the middle.
There we go. It looks good.
Did you guys? That looks awesome. That all looks great.
It's really good. So now that we have the popsicle sticks, we grab another rubber band, and now we rubber band this side.
And you
So-
should try and do it about 3 times again.
Yes, and the distance of the rubber band should be about the same as the other one. It doesn't have to be exact, just
Okay.
approximation.
Rubber band.
Yeah, so the side that doesn't have the rubber band yet, go ahead and rubber band it 3 times.
So it should be symmetrical, the rubber bands. Perfect. That looks really good, you guys. So the next step is you're going to place a new popsicle stick, so another decorated one, diagonally over the perpendicular stick. So this step is a little confusing, so bear with me. You'll take your new popsicle stick, and right over this perpendicular popsicle stick that you had in step 2, you're going to lay it over it, right over it. So it's going to be leaning on an angle, as if you're leaning against a chair. So it's going to lean on an angle. And we'll rubber band it in place, so that way it stays in place, because right now it wouldn't stay in place. It's holding in place with your finger. So you're going to place that decorated popsicle stick over the perpendicular stick, but since there's 11 popsicle sticks right here, it has to lay on top of it because it can't just lie straight down because there's stuff in the way. So this should be the topmost popsicle stick, so it's above everything else.
Yeah, so if we have it in a T, so our bottom one, this is our bottom one that we did, and these are the popsicle sticks on top. So upright, it should look like this. This is the bottom one, yeah, it's like this. And then we grab our new popsicle stick and place it on top, like for now.
So
And if we put it on the side, you can see the very bottom one and the top one that we just placed. Zion, I think yours is upside down. So just switch it upside down. Yes, there we go. Yes, so this stick should be on the bottom, and then this new one, we just place it on top. Yes, there we go.
Good, you guys.
How is everybody's looking?
Good. Perfect. Do you guys feel like you're ready to move on to step 5?
Yeah.
So now now that we have the incline, so the bottom popsicle stick and the top popsicle stick, we rubber band them together. So we place the rubber band right here. Again, the distance doesn't matter.
You're going to place the rubber band on the bottom where the two popsicle sticks meet. But don't put it too close to the edge or else it will just fall off. So see how there's a little bit of space in mine? That way the rubber band doesn't just fall completely downwards. You want to have a little bit of leeway. So now you should see that they're able to be rubber banded together, which allow them to stay in place. So now you don't have to hold it together with your finger.
So far it should look a little bit like this.
Here's a side view of it.
Can you show me yours again, Diane? So I think we need to change it a little bit with yours, Diane, because we need to take off one of the rubber bands, one of the ones on the side, and then one of the popsicle sticks that's horizontal, it should be at the very bottom. There we go, yes, yes.
Yeah, that's perfect.
So now we rubber band that side.
So you should have those 11 popsicle sticks kind of sandwiched in between it.
How's yours, Dita? It looks good. Nice job. Yep, that's perfect. It looks good. How's yours, Josiah? Can you turn it a little bit on the side, please? Oh, there we go. Yep, it looks good.
Good, you guys.
Perfect. It looks really good. Nice job. Are we ready to move on now or not quite?
Do we feel good about step 5, you guys?
Yeah.
Yeah? Okay, cool. Let's move on to step 6 then. So the next step is you're going to take a bottle cap. It can be from anywhere. Mine's actually from a milk jug, but it could be from a juice jug or milk or Gatorade. So wherever you can have a bottle cap, you want it to lay right on top of that top popsicle stick, and we're going to actually tape it together. So what I like to do to tape it is I like to first make a little tape bubble. So I take a little piece of tape And then I turn it around itself and make a little bubble out of it. So if you see, it's a little bubble. And then I'm going to put that bubble where I want to place the bottle cap. So I'm going to put it right here on top of that top popsicle stick. And then I'm going to take my milk jug, and you want to tape the flat side. So you want to have the concave inside facing up so you can place something inside of it. So you want to take the back of the bottle cap and you want to place it onto that tape bubble. And you can really press down on that to make it stay. And it should be right here. If you see, this is my top popsicle stick, and it's at the far end. So the end that's not rubber banded, that's where you're going to put the bottle cap. So you place that here, and I like to give it a little bit of extra support because I feel like it's going to fall off a little bit. So I like to take some extra tape, and I like to tape around the bottle cap too. So I take this tape, and I'm going to put it inside the bottle cap, and then I'm going to tape it to the popsicle stick as well, just to get a little extra support there so it doesn't come undone. So I tape it, and then I tape it around to the other side. So that way it's taped onto the bottle cap, onto the popsicle stick in multiple ways. So you can go over it a little bit if you want for that extra security measure. This is a hard step though. This step is imperative. So we're gonna spend just a little bit more time on this step, but it's super important for your catapult.
We have the bubble of tape. Dita?
Yeah.
So here's your bottle cap. One sec. So we place it on our popsicle stick or the bottle cap first, it does not matter. I personally just put it on the popsicle stick.
Okay.
And now we grab our bottle cap and just stick it on there. And just to make sure it like stays, I like to press a little bit of force.
Mm-hmm.
Yep, looks good.
That looks awesome.
Looks great. And now, just to make sure it doesn't fall off and to play it safe, we grab a little bit of more tape and place it on the bottom and around on the sides of our bottle cap. There we go. So it should be like this.
So you grab tape and you put it all around the stick and the bottle cap?
Yes, just around the sides, not up top.
Oh,
To
okay.
make it a little extra sticky.
Yes, just to play it safe. How's it going so far? It looks really good. Nice job.
Let me know if you guys have any questions on this step, because it can be a little tricky getting the tape to hit the bottle cap.
Okay, I messed up.
Are we ready to move on, or do we need a little bit of more time?
Little bit more.
A little bit more time? Okay. Let us know if you have any questions, okay, Dita?
Okay.
How's yours, Josiah?
Just screw it on because the tape and glue wasn't working.
Oh, it's not working?
So we're gonna screw it on.
Oh, you're gonna use glue? Okay. Glue also works for this, so if you have glue and would prefer to use glue, that also works. It just takes a little bit of time to have it dry before you can use it, but glue also would work very well.
How's yours, Diane?
I think mine's pretty good. Yeah.
It looks really good.
Yeah, that's awesome.
Okay.
It looks good, Dita?
Yeah.
All right. Perfect.
How you doing, Josiah?
So now that we have our bottle cap glued, we insert any item that we would like into our bottle cap. I have a quarter, so we could place a quarter or whatever you have on hand, any small object that can fit inside of your bottle cap. So just place it inside. And to see if it works, we're making our run. So what we've noticed is that to pull it back, it's best to pull it back from the actual popsicle stick and not the bottle cap. So we pull back the popsicle stick and let go for it to launch our object.
And then the last step is to catapult, but we're gonna wait just a hot second to do that. So we're gonna do something first before we start catapulting all of our objects. So this is just to get all of your objects prepped and ready for you. There's a lot of small objects that you can use as options, and we'll go over a bunch of common options that you guys may have around that you can use, but you can also be creative and launch anything that you would like that's safe. So before though, we're going to draw our predictions of how we think the object will be launched. So there's many ways that the object can be launched in the sky. It could go straight up and straight down. It could go straight out. It could go in a rainbow arc. So we want you guys to take out a piece of paper and a pencil or a marker or a crayon, and we want you to draw your predictions, and then we're going to talk about it. So we're going to give you guys just a minute or two to think about how do you expect your quarter to fly or your marshmallow to fly after you catapult it, and what would you expect to see, and draw that pathway out.
Do we have any predictions so far on how our object will fly once we let our catapult launch?
Yeah, does anyone want to share their picture, or how, or just verbally say how they would predict it to fly?
I drew something. It's not like that good
Yeah.
or detailed, but
Pretty good to me.
yeah.
It looks really nice. I like it.
Yeah. Awesome. So we can clearly see your catapult drawing, which is awesome. And then you think that it's going to kind of go in a curved trajectory. So it's not going to go straight up. It's not going to go straight horizontal. It's kind of going to do a mix of the two and go diagonally and be curved.
Yeah. Yep.
So, thank you so much for sharing it.
What is everybody else thinking? I can't quite see, Josiah.
Could you bring it a little bit closer?
So also the
I
same
think
for these.
Yeah. I think you have a similar idea where it kind of goes in a rainbow pattern. Is that what you're saying, Josiah? Awesome. That's a really pretty picture. Thank you so much for sharing it. And then Dita, if you would like to share too, you definitely don't have to, but if you would like to share your predictions as well, we'd love that.
Yeah. I think we'll only just launch a little bit.
That looks awesome. So we all have similar ideas of how we think it will go and what the trajectory will look at. That is really good. Thank you guys for all sharing your observations.
Yeah,
So,
great drawings.
they're all great drawings. I was actually pretty impressed with all of your drawings.
So yes, like you predicted, once we launch it, it will go in a rainbow pattern. So actually this type of graph is called a parabola. and the parabola is a U-shaped, and that's how our object will travel. When a parabola is a graph of a quadratic function.
So it'll go in that rainbow trajectory will be launched up, and then it's going to reach its highest point, and then it's going to start to fall back down in a curved fashion. So you guys were all spot on with your observations. So before we start experimenting, we're actually going to have you guys note and record your starting angle. So Leslie, you want to take over on how to record your starting angle?
Yes, so we grab our protractor. Do we all have our protractors handy? Here we go. Okay,
Good.
yeah. Now we grab our catapult. One second, there we go. And now that we have our protractor and our catapult, we place it right inside. It should look a little bit something like this. Looks good. Yep, perfect. Yep, perfect. So now we're going to measure our angle, and all of our angles will be a little bit different, but that's okay. That just depends on where we place the bands, but it's okay. So in my case, if I read my protractor, my angle is, it's 40 degrees. So if you go ahead and read the number that the angle up top from where your bottle cap is, that should be the measurement of your angle.
And we are going to be making a data soon. So if you want to get a new piece of paper and just write your starting angle on the top of that paper, the same page that you will make your data table with, that would be awesome. Just so that way you guys can remember your starting angle. So for instance, my starting angle is 35 degrees, which is slightly different than Leslie's. But like we said, everyone's starting angle may be slightly different. It's how you constructed your catapult and where you put the rubber band that changes where your initial angle is. So it is totally okay if it's not the same as everyone else's angle, going to be slightly different. We will mainly be talking about the differences in angles, so how the angle changes versus what the actual numerical angle is. But you guys should record what your starting angle is. And if you want, you guys can tell us what your starting angle is too.
Are we all able to measure our angle?
Yeah, I got 35 degrees.
Yay, perfect, me too.
Were you able to measure your angle, Josiah?
It was 31.
Yeah, I got 35 degrees too.
Oh, okay.
Nice.
Perfect.
Okay, so we're all in the same area. That's awesome. We have 31, we have 35, we have 40. That's perfect. They're all pretty similar. And like Leslie said, it just depends on where you put that rubber band to see how your initial angle changes. So those are some awesome starting angles. So we're on track to do great things. So next is, we're going to start our experiment. So this first part of our experiment is we're going to manipulate that launch angle that we're just, while keeping the object consistent. So for instance, there's so many objects that we could do. I have a dice right here. I also have a quarter on me. I also have a ping pong ball. I have some marshmallows in the kitchen I can grab. Whatever object you would like to do that fits, you could do a marble, whatever object that fits, that works perfectly well. We just, for these trials, we want to make it consistent. So we want to make it the same every single time that you launch it. And then you guys will get a chance to try all your objects that you have in your house. But for this starting experiment, we're going to keep the object consistent, and we're going to change that angle that you launch it at. So for instance, my starting angle is 35. If I push it down just a little bit, that's different. Push it down halfway versus if it down as far as I can. So we're looking at that difference in angle. So not what the actual exact angle is, but the difference. So Leslie can show it to you guys really well on her Protractor. If she starts at 40 degrees and she pushes it down a little bit to be at 30 degrees, then her change in angle would be 40 minus 30, which is equal to 10. But let's say Leslie pushes it down just a little bit more to 20 degrees now. So now it's halfway down. Well, then her difference in angle is 40 minus 20, which is equal to 20. So we're looking at the differences in angle and how that affects our results. So we're going to give you guys a few minutes, and we're going to do this too, where we're going to pick an object. I'm going to pick my die, and we're going to launch it while changing the angle. So changing how far we pull it back, whether we pull it back just a smidgen or whether we pull it back a lot. And we're going to see, how does that affect our results? How does that affect the distance traveled? And then I want to hear from you guys what you observed. So you guys can write down how far it goes to. Let's do it on the carpet.
How are your launches going?
So remember, it's easiest to pull back from the actual popsicle stick and not from the bottle cap itself. That just makes it easier to launch the object.
Feeling.
Have we noticed anything so far with our launches?
I pulled it down 10 and it hit the ceiling.
Oh, wow.
Feeling, whoa.
How are everybody else's launches going?
Yeah, how's your catapult working out for you guys?
Mine's good.
Yeah.
I guess. Yeah.
Do you see any differences in how far you pull down your catapult? So if you just pull it down a little versus if you pull it down halfway versus all the way, do you see any difference in your result?
Yeah, like if you pull it down like all the way, it has more of a chance of going farther.
Thank you, for sure.
I'd be interested in what objects you guys are launching, because you were given some examples, but do you think that it would make a difference if you're launching like a marshmallow, or another example you gave was like a marble?
Yeah, and that's a really good point, Maggie. And we're going to actually do that also later on. We're going to give you guys a chance to manipulate the object that you're using and see if that affects the distance traveled, if the mass of the object does have any impact on it. So if you guys are able to see that right now too, with knowing, oh, I'm using a heavy object and my friend is using a light object, and seeing how that changes too, that's really important to note.
So yes, like we mentioned, depending on how far down we press on our catapult, that will affect our distance traveled.
Yes. Does anyone else want to share any observations that they had before we move on and talk about what some of those results may have been?
Mine only went like a little.
What happened when you pulled it farther? Did it go any differently, or did it also still only go a little bit?
Went a little, but not that much.
And what object are you using?
A marble?
A marble.
So if you press it all the way down, what does the marble do?
It goes all the way up to the sky.
And if you just press it down a little bit,
Then it just goes a little bit, doesn't go all the way up.
right.
Cool.
So yes, like we noticed, all of our predictions were appropriate. Depending on how far down we pull it, that will affect the distance traveled. And like we mentioned earlier, that will affect the parabola that's created, or the U-shaped graph. So for example, if we pull it down all the way, so let's say like I'm launching an object, it goes all the way up, 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 and in Josiah's case, it hits the ceiling. So it's a really big U. But if we just pull it down a little bit, and then it just, oh, that was a little bit further down. Let's try a little bit down. A little bit, then it'll go just whoop. It'll be a smaller U, so a smaller parabola.
And what we also noted here is, if you see in the picture, firstly, how do these angles that we have right here, so the 60 degrees versus the 45 degrees versus 30 degrees, I want you guys to think about it. How do these angles differ from the angle that you saw, wrong side. The angle that you saw on the previous slide, which I'm going to show you the picture of. The angle right here. So this weird symbol right here, that's called theta, and that's the notation for an angle. So the angle that's measured here is that pullback angle that you guys initially measured. But how does that angle, so that angle between these two popsicle sticks, how is that different than the angle that they illustrated on these images right here? So I want to hear your guys' viewpoints of how do you think their angles are different? Do you think that they're the same angle, or do you think that one is measuring something while the other is measuring a different thing? Would anyone like to share their thoughts? And it's okay if you don't know also. That's why we're here. We're going to learn about it. So it's okay if you're not 100% sure about what you're saying. Would anyone like to share their on it or their guess, their prediction of what it may be? So this angle right here, the one that's notated as theta, that's like we said, that's going to be the pullback angle. So it's going to be the angle that affects the force of tension on the rubber bands that we'll talk about in a little bit. So that's that pullback angle versus the angle that's on those illustrations. That's actually the angle of the projectile, angle of the object when it goes in the air. So that 75 degrees means that the angle went 75 degrees in the air, measured from the ground when it got launched upwards. So they're measuring two different things. As you can see in this illustration, it gets a little confusing, right? Because you think bigger angle means bigger distance, but that's actually not necessarily the case. In this case, bigger angle means bigger distance. So the bigger the theta was, means the larger it will go. But this number right here that they're measuring, since it's a completely different angle, it actually doesn't correlate to a larger distance. So if it's 75 degrees in the air, let's take Josiah's example, and it hits the ceiling, it's not going to go as far as if it's launched outwards, more horizontally. So if it's launched vertically higher, it won't go as far. Does that make sense, you guys? Do you have any questions on that? Because that's kind of confusing. So when it's launched more vertically, it goes higher in the air, but it doesn't go a larger horizontal distance than if it's launched more horizontally. So it has a smaller angle to the ground, as you can see in these two illustrations right on the slide. Let me know if that's a little confusing and if we want to go over it more, or if you have anything to add to that conversation. Okay, do you want to move on? Can you give me a thumbs up if you're ready to move on? Thumbs up, thumbs up. Okay, perfect. The experiment continued. So all these images, all the smorgasbord of images, those are just different objects that you can launch. So for instance, we have the marble is launching, or you could do a cotton ball, or you can do a dice, which is what I'm using. Or we have marshmallows or pennies, so tons of objects, and you can also be creative with it. So the next thing that we're going to do is we're going to launch an object multiple times. So you're going to pick one object. So for instance, I could pick a ping pong ball for this one. And you're going to put it inside your bottle cap, and you're going to launch your catapult. Now what you're going to do is you're going to record the distance for each trial. So if you have a ruler on you, that would be really handy. For instance, my ruler is part of this little thing right here, but I also have a separate ruler that I can use. And you're going to measure the horizontal distance that the object goes. So if I have a catapult and let's say it doesn't go too far. Let's say it only went to here. That would kind of not be awesome, but sometimes it happens. Then I can measure the distance from where it catapulted to where it ended up using my ruler. And then from there, I can record that distance. So you can do it in inches or in centimeters, whatever you'd prefer. Just keep it consistent each time. So if one time you measure it and you're like, oh, it only went 6 inches. And then the next time you measure it and you measure it in centimeters, you should do it in the same unit. So either pick inches or centimeters. And then you're going to record the distance in your data table. So if you look on the bottom right of our screen, it has a little example of a data table. It does not need to be exactly like that. You can do your data table however makes most sense to you. That's just an example that you can follow if you would like, and you can record how the distance goes for that object. So once you've done about 3-ish trials for your object, you're then going to switch to a different object. So now I'm going to use my quarter, and you're going to put that in there. You're going to launch your catapult, and then you can record the distance for that. And then once you do your 3 trials of your second object, you can do a third object, how far it goes. So then we're going to ask you what observations you made. So how did changing the object affect your final distance? Does that make sense? So that was a lot right there. Any questions on what we're going to do? We're going to launch different objects a few times and record the distance that it goes.
So in my case, I'm going to start with a cotton ball. So I'm going to place it in my catapult and then just launch it a few times and try to record the distance. Oh, that fell down. But then I would launch it and then record the distance traveled. I don't have a ruler, but I do have measuring tape. So I would just measure the distance from the catapult to where it landed. In my case, it's 8 inches. How's it going with everybody?
And we're definitely going to give you guys some time to do this. So you can pick whatever 3 objects you would like to do and then launch it and record the distance for each object. To see how, does the object affect distance at all? I don't know, we'll find out.
And throughout this, do you think that we should have our pullback angle the same or different each time that we launch our object? So for example, if I'm using a cotton ball, a quarter, and a penny, for each trial, should I launch it about the same distance, the same pullback angle, or should I change it up?
It's a really good question, Leslie.
What are you thinking?
Guys, is it important to keep the angle consistent, or does it not matter?
I think it's important to keep it consistent because then you could end up with like different results and it wouldn't really make sense if you have different angles and different results.
That is a perfect explanation. So in an experiment, you can only manipulate one variable at a time. So angle was the variable that we manipulated in the last slide, but now we're manipulating the object. So if we're manipulating the object as our independent variable, that means that angle has to stay consistent, because if you manipulate both of them at the same time, you won't be able to analyze the results because you won't know if the further distance is due to the object's mass, or if it's due to the angle, or if it's due to both. You have no clue what your results are about because you're manipulating more than one thing at once. So you want to keep that angle as consistent as possible. So if you go, I'm going to pull it back halfway, then you pull it back halfway each time you do it, even with changing the object. That was a great explanation.
Yes, thank you for sharing, Diane. So like we said, with our different objects, we should try to launch them at about the same angle. So if we're doing a smaller angle, just keep it like this. Or if we want to go all the way down, we go all the way down, but just all the way down with all of the objects. Just to make sure our results are consistent. So we can go ahead and do a few launches with that and see what we notice.
That quarter went pretty far.
Yes, my objects keep falling off my desk.
My ping pong ball went real far. That was my best catapult launch yet. That was a personal record for me.
Have you noticed anything with your launches?
Are your guys' launches going well?
Huh?
They're going good, Josiah?
So earlier I launched my cotton ball and did it a small pullback angle. And like we said, it only traveled 8 inches. But if we try maybe our penny and a small pullback angle, do we think it'll travel? How do you think that will affect our distance traveled? Let's see. Uh-oh. Try it again. Do you have any predictions on how the distance changed in difference to the cotton ball?
Well, probably like heavier objects probably don't travel as far as lighter objects, like a penny compared to a cotton ball. The cotton ball will probably travel farther. I'm not sure.
Yeah, yes, I think that's great. And I noticed that as well with my cotton ball because it did travel a little bit further. As we said earlier, it traveled 8 inches, but now that I launched my penny, it only traveled 6 inches, but I don't know if you were able to see it on camera, but it went a little bit higher.
Yeah, you're going to need a larger force to launch a heavier object. So if the object's more massive, you're going to need a larger force. So for instance, a larger pullback angle, granted from the force of the tension of the rubber bands. You're going to need a larger force in order to launch that object. And then once that massive object is launched, it's going to experience a larger force due to gravity because it has a greater mass. So it's going to be pulled down to the earth and the ground faster than maybe a light object like a cotton ball would be. how are we doing with our launches, you guys? Do we want some more time to experiment a little bit more with our launches, or would we like to move on? How are we feeling?
I think we could move on.
Josiah, how are you feeling with your launches?
We can move on.
How's it going, Dita? Are we ready to move on, or?
Are you ready to move on, Dita?
I think we can move on.
Awesome. Thank you, Dita. Okay, so experiment continued. So now we're going to launch an object, and it can be an object of your choosing, and you can change what the object is. So if you start with a ping pong ball, you don't have to end with a ping pong ball. But you can launch any object of your choosing, and we're going to set up a cup tower, and we're going to try our best to knock down our cup tower. So I'm going to show you guys a sample cup tower of how you can create one, but I want you guys to be as creative as you can with how you're going to create your cup tower. So you definitely do not need to follow how I'm doing the sample one. So for instance, for the sample, I'm going to do 3 cups, and I'm going to build that as my base. So they're going right next to each other. Yeah, and you guys can follow along on how to build your sample cup tower, and then you guys can modify it in whatever way you would like. So I have 3 cups right here. Awesome. And then I'm going to take 2 more cups, and I'm going to put them right on top of the 3 cups. And then I'm going to take 1 last cup, and I'm going to put them all the way on top. So that's my very simple cup tower. It's just a pyramid. It's a 3-2-1 pyramid, but you can do whatever you would like for your cup tower. So you can get as creative as you want for your cup tower to try and knock down as many cups as you would like. So I have a bunch of, we have images on the bottom of the slide of different sample cup towers. Ways you can make it. Yeah, fun fact, the Guinness World Record for cup towers, that's 57,000 cups. Isn't that crazy? So we want to see if in this workshop, you guys can surpass that. So who thinks that they can build more than 57,000 cups by the end of the workshop? I want to see it.
Yes, that would be great to be a part of. And then we could launch our catapult onto it and see it slowly fall down.
So for this part of the experiment, you guys are going to create whatever cup tower that you would like and whatever design you would like. And then you're going to try and launch your object. So it can be whatever object you want. And you're going to try and knock down all those cups, kind of like bowling, how you knock down all the pins with your bowling ball. You're going to try to be as successful as you can. And you can use your cup tower. You can make it super far away. You can make it close. So you can alter where your cup tower is and how you're knocking it down to be the most successful. And then I want to see your guys' cup towers and how successful you are. So I want to hear how it goes.
Okay.
Yeah, so now that we have our cup tower, we can continue launching and see if we're able to throw the cups down. And it may take some practice, because the first few times I did it, it was definitely a little bit difficult.
There's going to be a little bit of trial and error to see how far away you need to have your cup tower to be successful in knocking them down.
yeah, no. Mommy?
How's it going with your cup towers?
I'm short by 1 cup.
That's okay. Have we been able to throw down any cups yet or not quite?
I missed.
Oh, nice. Nice job, Hannah.
Thank you, you guys.
How's it going, Josiah, with your cup tower? Oh, wow, I like your cup tower, Tita.
Thank you.
What different objects are we using to launch towards our cup tower?
What are you doing, you guys?
Used 21.
Oh, I think we lost Hannah. That's okay. I'm sure she'll get back on soon. So have you been able to throw down any cups yet or not quite?
We got a message in the chat from Dita. It says that she used 21 cups. That's a lot of cups.
Oh, wow, yes. I think with all of our cups together, we can get closer to the world record.
I'm sorry about that, you guys. I think my internet like cut out for a split second. We're good. We're back. I will share my screen again. I am very sorry.
So I've been using my quarter, and I've noticed that that's a little bit more successful in throwing down the cups than the cotton ball that I've been using as well.
Yeah, the cotton ball is probably a little too light, I feel like.
Yes.
Yeah, I used my quarter and that was successful. How are we doing with knocking down our cups? Are we doing good? Are we getting some successful runs in there with knocking down our cups? Dita, how is it going for you? Are you having any successful trials?
Yeah.
Yeah, that's awesome. Yay. Perfect. We are going to give you guys 1 more minute and then we're going to move on. But you guys are more than welcome to continue like manipulating your cup tower and making it bigger and bigger and bigger once this workshop is over. Who says our catapult fun has to be done once we're done with this workshop? I know I'm going to continue experimenting and making the biggest cup tower that I personally can in my living room and see if I'm successful at knocking it down. So
Yes, I'm thinking the same thing. I'm thinking
Yeah.
of challenging the world record before
Right?
summer is over.
I am not done with my catapulting. So yeah, we're just gonna take a momentary break and then you guys can get back to it too. So we're going to explore a little bit of the STEM concepts that we explored in this workshop. So first thing I want to ask you guys, and then we'll talk about it, is energy. So that's a really big concept that we're exploring when we focus on catapults. What types of energy are you guys aware of? And what types of energy did you observe in this experiment? So there's many different types of energy, but what types of energy do you guys just know offhand? Like, can you list any types of energy that you know of?
And potential energy.
Potential energy, that is an awesome one. That is a great example. Any other types of energy that we know of? Do we know the energy that makes you move?
Kinetic energy.
Yeah, kinetic energy. Perfect. Anything else? Any other types of energy? That's okay if we don't know any other types of energy. We'll talk about it. So would you mind sharing how you observe potential or kinetic energy during the catapult experiment?
Like the catapult, like it gets potential energy when you pull back the thing, and then you release it, and that's like kinetic energy, and then you can like catapult like anything, like a coin. Yeah.
No, that is awesome. That is a great explanation. Does anyone else have anything that they would like to add in to that energy? Okay, so when we're talking about energy, there's this thing called conservation of energy, and that's a really important principle that really says that we cannot make or destroy energy. So the energy that we have at the start of an experiment, we have to end with the same amount of energy. We don't just randomly create energy, right? And it doesn't randomly get destroyed. So we see different types of energy when we're utilizing our catapult. For instance, you have the chemical energy of your muscles pushing down the popsicle stick. So when we're expanding and making that angle as large as we can, I put a little bit too much force on my catapult. So when we're making the angle larger, we're using chemical energy from our muscles to really pull down those rubber bands. And then you're also using potential energy. So you store elastic potential energy in these rubber bands, and that's going to give the energy to transform into kinetic energy. So since conservation of energy states that energy can't be made or created or destroyed, it just has to be transferred in different states. So you start off with your potential energy from the rubber bands. That tension that it's giving you creates potential energy, and that potential energy will turn into kinetic energy once the object's launched, which allows the object to move, right? We can't move without kinetic energy. So that potential energy that's stored in the catapult, that transforms into kinetic energy of the launched object. And then I guess I answered for you guys what conservation of energy is and how it was demonstrated in the catapult, right? The forms of energy that gets transformed. So the energy changes states, but it doesn't just magically appear and it doesn't magically get destroyed. It stays the same, it just changes form. So you go from chemical energy in your muscles and elastic potential energy to then kinetic energy. Now the next big STEM concept, a really important concept in physics, is forces. So does anyone want to share what they may know about forces, like any background knowledge about forces or what forces they see interacting with the catapult? Does anyone have any ideas on forces? Did we see forces in this experiment? And where did we see forces?
There was gravity.
Yes, so gravity is a really important force, right? We would not be able to be standing here or anything without gravity. So gravity is a huge force, so that's awesome. Any other forces that we witnessed? Anyone would like to share? So Dita, Josiah, anyone? Yeah, we got to think about it, right? So let's just take 20 seconds to think about what forces we might have seen. So think about what we know about forces, if we know anything about forces. If not, that is totally okay. It could be a completely new concept that we're learning today, which is super cool. So do we know anything about forces? Where have we seen forces interact? So let's just take a little minute. Let's think about it. I have to think about it too. Okay. So there's two main types of forces that we're going to experience. The first is the force due to tension from the rubber bands. So as you pull back this catapult, the rubber bands are stretching, and that creates a force due to tension. That force of tension is what catapults the object and points upwards. So that's what launches the object, is that force of tension that builds up as you press down. It builds, it builds, it builds, it builds, and then it releases. So that force of tension is causing the object to accelerate upwards. But then the other main force is the force of gravity, which was mentioned. So that force of gravity is always pointing downwards on ourselves. So you have to the object to accelerate upwards, but then once the object is in the air, it doesn't stay in the air. It experiences the force of gravity, which is pulling it downwards back to Earth. If the object didn't experience a force of gravity, what would happen? Does anyone have any idea what would happen? So what if the object only experienced a force of tension and never experienced any gravity? Do we have any idea what would happen?
It's forever.
Right? Yeah, it would just go on forever. Nothing's ever bringing it back down to the ground. You would just see your ping pong ball just fly off into space and you would never get it back again. It wouldn't come back to the ground. So that force of gravity is pushing that object downwards. And that's why it creates that rainbow arc that we talked about at the beginning of the workshop. Because you have that force of tension pulling upwards that causes the object to launch up. But then you have gravity pulling it down and pulling it down and pulling it down all the way to the ground. So the force of gravity takes over and causes it to come to the ground and hit the ground. That's really great, you guys. So the next STEM concepts that we have are some math concepts.
Yes. So far, I think it still blows my mind how there are several science and math concepts involved in so much fun. And at first, we might not have realized it. So how did the path, when we launched the object, what did we notice about the path that was traveled? Like we mentioned earlier, which shape did it follow?
A parabola.
Yep. Perfect. A parabola. Yeah, so like we mentioned earlier, a parabola is a U-shaped graph. It could be upside down or a regular U. In our case, it's an upside down U. So it'll always be in a parabola. And how did the pullback angle, so depending how far down or how far a little bit we pull down our catapult, how does that affect our parabola that we noticed in our launches?
It affects the distance the object travels.
Yep, perfect, yes. So if we press the popsicle stick lower, so meaning that it's a larger angle, then the object will be launched further away. So it'll be a larger parabola, like you mentioned, Diane. But if we just push it down a little bit, it'll travel right here. It'll kind of go like this a little bit. So it all depends on how far down we decide to pull down our catapult. Does that make sense? Do we have any questions?
Yes, any questions on anything of the concept that we explored? So any questions on energy or forces or parabolas? Any questions that you guys may have for us? Okay, so our very last slide is thanking you guys. Thank you guys so much for joining us in catapulting math and science to new heights with us. I had a lot of time with this workshop. This is my first workshop that I've taught, so it was really exciting, and thank you guys for joining us with it. I had a great time building catapults with you guys. We wanted to open the floor to you guys just for a little bit if you had any questions about STEM or catapults or the workshop, or any questions about us or our majors or anything like that. The floor is open for you guys. So yeah, just let me know if you have anything that you would like to know a little bit more about Leslie or myself.
Yeah, sir. Go ahead, Josiah.
Yeah.
Yeah, thank you so much, Josiah.
Thanks for joining us.
Yeah. Does anyone have any questions that they would like to ask?
No.
Cool.
Yes, I'm excited perhaps to take it outside and build my cup tower there with my catapult, and perhaps in the future make an even bigger catapult. I'm excited.
That's a great idea, Leslie. I can make a huge tower then.
Right.
I'm excited. So yeah, just because this workshop is over doesn't mean your catapulting has to be over. After this workshop, you guys can go and make a ginormous tower, and then let Maggie or Meg know if you guys go over the Guinness World Record or 57,000 cups, because I want to know if we go over the world record. So yeah, thank you guys so much.
A big thank you to Hannah and to Leslie for leading this workshop. It was so much fun. I really enjoyed sitting in on it with you guys. And thank you so much to all of our youth who joined as well. And I hope that you learned something and had so much fun with us too.